processes, and the title of the topic is Detecting Frequently Recurring Structures in BPMN tools.
Hello everyone, thank you for the introduction. My name is Marigianna Skouradaki. I work for the Institute of Architecture of Application Systems for Leymann.
Can you move the microphone a bit more?
Okay, yes, okay. I'm going to present you my work, which is detecting frequently used recurring structures on BPMN to process models. The motivation for this work is that we need to define the workload for benchmarking BPMN2 engines. So for this we have collected a very large collection of BPMN2 process models. It's a collection about 1,000 or 700 process models roughly. And for this we want to take out the statistics that will basically create a realistic workload for benchmarking BPMN2 engines. Since the only data that we got from the companies is the structure of the process model, so no log information or no information about the instances rate used for these models, we are focusing on the structural analysis of the models. For this, we apply graph isomorphism techniques to extract the recurring structures of the process models, and then out of selected process fragments, we will apply composition criteria to create again deployable artificial models which will constitute the workload mix. This brings me to today's motivation. I will first present you the existing techniques in process model matching. I will discuss the theoretical framework that was set for this work, and then the algorithms that we are currently running, a validation and discussion on the results, and finally conclusions and outlook. Before I discuss the different techniques in process model matching, I would like to discuss the nature of our collection. We basically have a lot of anonymized models. That means that most of the models do not have label information, but the labels look like A, B, C, D. So we don't know what job actually each task does. And most of the models are mockups, which means they are not currently in their executable format. So for this, there are currently existing matching techniques. For example, the text matching technique will take the labels of the process models. Here we can see a buy task and pay and payment tasks. These tasks are basically matched according to their labels, and we can see that we can suspect that around this area the process models match. As I discussed, this cannot be applied in our collection because our models are anonymized. Another technique is to do behavioral matching. This means that we basically execute the process model. This will create a process log that is then taken and compared with other logs created by other models. In the areas that the logs are presenting similar behavior, we suspect that the original models match. Again, this technique cannot be applied to our collection because our models are not executable. This brings me to structural matching. This is basically to see which parts of the models are structurally equal. Techniques that currently work in this area are also dependent to text labeling, which, as I discussed, we do not have available. Or they are doing graph edit distance techniques. And these techniques basically say that we need to start from the beginning of the graph and see how many insertions or deletions or editing we have to do to reach one model from the other. This technique is basically more successful when the process models are different versions of each other. This brings me to graph isomorphic techniques, which basically take a graph and see the similar points. An isomorphic graph is basically a set of nodes that are connected with edges on the same way. However, as you can see, this can take different formats, and for this reason it is very difficult to detect the similar parts. For this reason, most people are unwilling to apply graph isomorphism techniques, and it is cited that this NP complete problem, which means we cannot calculate how much time it will take for very large graphs. However, I was lucky because BPMN models are very special types of graphs. They have directed edges and they have attributes. And by attributes, I don't only mean the labels, but also the structural information of the BPMN2 elements. For example, start events, tasks, exclusive or parallel gateways. And this gives me information to create algorithms that, according to the bibliography, can run with lower complexity that can even be polynomial. This brings me to the theoretical framework I have set. For my collection, isomorphic parts can be nested with each other, as you can see in this example. Yes, the green frame will have nested the blue frame. They can appear in different positions. For example, you can see these two subgraphs appearing at the beginning and at the end of different process models. Or they can be partial similar, which is quite a trivial attribute. And this means that at some point, the subgraphs start connected with different parts. For this, I needed to define the process fragment, which is defined primarily from a colleague called David Zoom. He defines process fragment as a piece of process model. It has loose completeness and consistency. Its existence of process graph element is possible but not imperative, and it must have at least one activity, and there must be a way to convert it to a complete process graph. I have extended this definition at 3 main points. This definition is not necessarily related to a complete process model, why I need the process fragments to exist in at least 2 process models. Starting point is not defined. While as we will see later, I need definite starting points for my algorithm. and the existence of a split or merge node or even event is optional. So for this, to extend this definition, I have I have defined the term checkpoints, which I will discuss later with an example. Checkpoint can be a pre-configured type of a node that is used as a start point to my process fragments. This means that the user says, for example, I want all start events to be a starting point for a process fragment, or I want all gateways to be as starting points to a process fragment. And this will basically give an execution time boost to my algorithm. As a relevant process fragment, I give the extended definition of the process fragment. It has to exist in at least k business processes. It has to start with a checkpoint. It must contain at least n nodes including the checkpoint. And finally, it must contain one activity or, in terms of BPMN, to a task. Now, to explain these definitions, I have set or configured the checkpoints as every event or gateway in the process model, and it makes exactly these elements. I say that it has to be existent in at least 2 process models, and it must have at least 3 nodes. Starting from the beginning of the process model, the comparison, I take the first 2 start events and I check if this is a relevant process fragment. This is not a relevant process fragment because it has a starting point start event, but it doesn't contain 3 nodes as it is set in the configuration. I proceed with the traversal. For the same reasons, this is not again a relevant process fragment. And to the next step, I can see that I'm getting the first relevant process fragment. Coming now to the algorithm, again I keep the same configurations and I will start traversing and comparing the process models from the beginning. This will basically check the source and the target of every sequence flow that participates in the traversal. So in this case, we take the first sequence flow. We check if the source and the target structure is the same. So in this case I have a start event and a task. So it's okay, I proceed with the traversal. Now again I have a task and an exclusive gateway. This is also matching, so I proceed with the traversal. And now we have splitting. Now in the case of splitting nodes, I have to check all possible combinations of the paths. So in this case, I will take the lower part, the upper part of the both models. It's also an exclusive gateway with a task. This is a matching types and I proceed. And here we see that it's a task with exclusive gateway and 2 tasks. This will basically stop the regression of this procedural call and will return this branch as matching. Now I was in a splitting point, so I need to go back and check the upper part of the first model with the lower part of the other model. This is still again matching points. And here the points are not matching. So in this case I will return this part. Proceeding likewise for the rest of the combination, so the lower with the upper part. I have match and again a match. And in this case it's 2 tasks to a task and an exclusive gateway, so they don't match and I return this. And proceeding likewise, I return this branch. At the end, I have matched all these branches, and by putting them in a set, I basically get this process fragment as a match. This will basically need to be done for all the checkpoints of the first process model to all the checkpoints of the other process model. The checkpoints basically are serving the goal that are reducing very much the complexity, because I do not need to check the tasks every element with each other, and some comparisons will stop the rehearsal very, very fast. This algorithm will still not work for cycles, however, so it's only working for cycles without, for process models without cycles. Coming now to the creation of the process fragment collection. In this case, I need to count how many times the process fragment appears in my collection, so that I can know the appearance rate of every fragment. So in this case, I apply again this graph isomorphism technique for every saved fragment in the collection, and if I find it, yes, I increase its counter attribute to +1, and by this way I keep the statistics that will be afterwards useful for the workload creation. Coming now to the validation, I used this technique to 43 BPMN2 process models as a subset of my collection. They come from the BPMN2 standard example processes and some models used in a research paper from Pitts and Betzel. These models were compared with all other models except for themselves, and we didn't have any duplicate comparisons. So when a model is compared with the other, it's not compared again. This led to 903 comparisons, and afterwards 1,544 non-filtered relevant process fragments. Non-filtered means that I didn't do any filtering to the duplicates, so all the duplicates were at the first run saved in the collection. When I started to rerun the algorithm with filtering the duplicates, I ended up with 259 relevant process fragments, which is basically 83% of the decrease of the results. For the resulting fragments, only 54 of them appeared more than one time. And for this, we get the median as a threshold, which was the 14th fragment. This is basically, the median helps us to define in the set which fragment is the most representative. In the 27 RPFs, 27 relevant process fragments remain above the threshold. For simplicity reasons, I only included 9 of these fragments. These are the most occurring fragments. As you can see here, for example, this was found 178 times. This counter means on how many comparisons this fragment occurred. The results that we can draw for, the conclusions that we can draw for this are basically that, as you can see, for 3 edges, the structures that we can retrieve are very simple, so I suggest that in future runs I run it for fragments that have more than 4 edges. We can also see that the parallel gateways are appearing in a lot of fragments, and that we have a lot of fragments that are branches, but only the one branch of the fragment is basically appearing. That means that the logic is different for the rest of the branches in the model. And finally, for the cases 7 and 9, we can see very complex fragments appearing a lot of times. This basically gives us the idea of our collection that a lot of process models were different versions of each other. Running this results to a collection of thousands of models, we expect that we will not have this incident so much. So to conclude, I have presented the extension of relevant process fragment discovery algorithm for getting the duplicates and counting. I have evaluated the approach with 43 BPMN2 process models. We can draw conclusions on the frequently used structures on our collection and on the collection special characteristics. And as future work, we extend to run the algorithm for the complete set of BPMN2 to apply to the greater collection we have, and implement the whole prototype that I presented as motivation for the synthesizing methodology. Thank you very much. I will be happy to take questions.
Thank you for the presentation. Before I hand over to the audience, one question for me. I'm not exactly sure if I caught the general goal of your structural analysis, and all your examples were focused on the structure, but not on the semantics of the actual operations, right?
Yes.
So, if you have a structural match between two workflows or BPMN processes, what does it tell you, and what do you do with that?
So, I go back to the motivation point. So this is basically for developing a benchmark for BPMN2 engines. For this, we need the structural information to know, for example, how the engine will react in the parallel structure situations, or in how the structure of the BPMN2 will affect the engine. That's why I'm doing this.
Okay. Any questions from the audience?
Possibly a little bit stupid question, but if you guys right from the beginning of your talk, you are doing the analysis based on the log files, right?
No, I said I cannot do that.
Oh, sorry. Okay.
I'm interested in, did you find any patterns which are occurring very often or which are very prevalent and which are much
it's a work in progress, yes.
Okay.
My question is just the extension of the previous one. You said you recall the purposes of doing your work. Can you please tell us again the potential benefits, outcomes of this analysis, or building this repository of occurring structures? The benefits.
The outcome of doing this structural analysis.
Yeah, let's assume that we have it already, that it's not being done on the hard-coded process, but on the real-life processes, and then?
Yes, then I get a lot of information on the characteristic of real-world collection, and out of this I can combine it to get realistic workload for the BPMN2 engines. So the current situation is that everyone will pass models that is convenient for their engines, but maybe not applicable in real life. So when you extract the information from real models and synthesize again out of it, then the workload will be more realistic to stress real life situations.
So you mentioned that you want to extend it to the complete set of BPMN. 2.0, so that means the cycles have not been included yet.
The cycles have not been included, and currently the tasks, for example, of BPMN 2 are faced as the abstract class, so I do not do a comparison between human task or received task or...
So that means later on you want to distinguish also those tasks.
Yes.
Okay, thank you.
I have a question regarding those cyclic BPMN models. You said your algorithm does not work at the moment, did I sum that correctly? So in terms of you don't get the correct results, or it does not stop? Or
It's an
so,
infinitive loop, basically, for these models.
Sorry?
I get infinitive loop for these
Okay, you get
models.
infinitive loops. So I thought maybe that just the complexity is too high and you get in this details.
No, but it cannot
Okay.
target it. The traversal is wrong, basically, for this type of models.
Okay, thank you.
More questions? Yes.
I just want to ask regarding the samples that you had from what industries and areas were the companies that provided the models? Because I guess if you want to do benchmarking, it should be, the scope should be general enough.
We have a lot of models from industry. Am I allowed to say the companies? Yes. IBM gave us a lot of models. I have from research projects. SAP gave us process models, so it's from research and companies also. It's a wide set. There are already published papers on the analysis of the collection, basically.
Okay, then thanks for the questions and thanks again for the presentation. And our next speaker is ready to set up already.